Morning, everyone. So I'm Jesse Santos, software engineer from Analog Devices. So previously I was a systems integration engineer, and now I'm working on software engineering. And I'm taking on projects that involve machine learning and signal processing. So to start off, we all know that AI is now everywhere. Actually, it's everywhere around us. But the difference, one thing that we should be mindful about is the difference between big machines and little machines. So big machines have unlimited, plenty of resource that it has to accomplish its task, while little machines are constrained devices. So it may be constrained in compute power, energy source, and also cost. And then one of the little machines that is present everywhere now is cameras. So imagine a camera system or camera module that not only captures photos, records videos, but it also can analyze on its own. And then going on to my topic, the time-of-flight system. So this is what a typical time-of-flight system looks like. So we have the analog front end that consists of the illumination module and sensor module. And then going on to depth processing, that is usually done by software. And then it is passed on to the software end as DK, so to interface the hardware and the user applications. So what we did was create a hardware depth engine dedicated for that sensor module, and then pair it up with a microcontroller with neural network accelerator. So the user receives not only sensor information, depth information, but it also receives an analysis of it. So doing it with ADI hardware is pretty simple. ADTF3175 is a time-of-flight module with built-in hardware depth engine. And then that data is passed on to MAX78000. So that's a microcontroller with neural network accelerator on it. So some pre-processing is done inside the microcontroller to mute the background. And then a classifier was implemented to extract what type of object is present inside the frame. And then developing it on MAX78000 is pretty straightforward. We have a framework that is dedicated to it. So there are 3 stages in this framework. So the first one is training, second is synthesis, and then the third is deployment. So training the model is largely based on PyTorch. And then we have synthesis that is its purpose is to convert the Python weights and biases, or the Python-based weights and biases, and converts it into C code that can be flashed on the MAX78000 hardware. Then the deployment is where the interface between different hardwares occur. So in our case, that's interface between the MAX78K and then the ADTF3175. Going on to the CNN model. So we used SimpleNet in our example application because SimpleNet is a relatively small network, but its performance is relatively on par with larger data sets such as ResNet and VGGNet on CIFAR. And then the point cloud that we trained this model on, or the data set that we trained this model on, was on point cloud data set. Its source is point cloud dataset, and then we transformed it into a depth map dataset using Open3D. So during the training, so these are the hyperparameters that were used during training. And then at epoch 30, quantization-aware training starts. And then on epoch 44, that was where we found the best checkpoint for it. So the training accuracy on that is 98% with a validation accuracy of 94%. And then going on to the confusion matrix, we saw that the highest or the best performing classes were bed, chairs, monitor, sofa, and toilet, while the worst performings were desk and dresser. So desks were misclassified as tables because desks are also tables, and then small dressers are misclassified as nightstands because of when you look at it, really looks like a nightstand on depth map. Okay, so going on to the inference, so there are three major things that we looked on inference. So that's the accuracy, time, and energy. So, and then the classes that we tested inference on were four. So chair, monitor, sofa, and table. Those were the classes that are present in our office. So the inference accuracy for the chairs and the inference accuracy for the classes were relatively 80% and above. And for the time, so 14 milliseconds were the average inference time with a deviation of 0.14 milliseconds. Then that translates to 71 images per second of inference. For the energy cost, so kernel loading was 210 microjoules of energy, or cost 210 microjoules of energy. But that's just a one-time occurrence, so you only do that one time. So what we're really interested in is the input plus inference energy cost. So that is 360 microjoules of energy, or about 35 milliwatts on peak activity. So the takeaway there is, so Max78K is a great tool for low power edge machine learning on the edge. And then when paired with ADTF3175, it complements well for hardware accelerated depth processing. So future work for this to improve the system is expand the data set. So it can be done by gathering multiple perspectives from the point cloud data set. And we can also try to capture real images of the time of flight module. All right, so thank you for your time.